constant velocity motion experiment to understand Newton's second law. The goal is to create a computer model of constant velocity motion based on Newton's second law and compare the model to the position and time data gathered by observing the motion of a black squash ball with assumed constant velocity. Newton's second law states that if an object is set in motion with an initial velocity v sub I, its velocity v sub f attained after a short time interval delta t is given by the equation v sub f equals the initial velocity plus the ratio of the net force to the mass of the moving object times the time interval delta t. In the experiment for gathering position and time data, I used a standard black squash ball. I recorded the motion of the ball rolled on an indoor hardwood floor with a wooden yardstick placed behind the ball's path, then uploaded the MP4 video into the tracker software program to analyze the motion. Since the ball was rolled from the right end of the picture window to the left, I set the XY axis such that the direction of motion of the ball followed the negative x-axis toward the left starting at the origin. I tracked the ball along several frames of video to create a position versus time graph in Tracker. I then transferred this data to Google Spreadsheets. Here is a video of my experiment. This is a screenshot of the data generated by Tracker when I tracked the motion of the ball frame by frame, as you can see over here. It generated this graph with a negative slope indicating motion from the right to the left end of the video in the negative x direction. This is a position versus time graph generated by Tracker and the data output time and position in 2 columns. For the computer-generated model of constant velocity motion, the goal was to create a simulation of constant velocity using the same ball. So I had to make an assumption of an ideal setup, that is all external forces acting on the ball such as gravity, air resistance, and any other forces like friction or any other unknown ones cancel each other out so that the net force is equal to 0. I set the F net value equal to 0 in the Python code so that it has no bearing on the final velocity in Newton's second law equation. When you set F net equal to 0, the final velocity equals the initial velocity, creating a simulation of constant velocity motion. To set the initial conditions of motion in the program, I use the position and time generated from Tracker from the first 2 rows of data and initialize the value of V sub I to negative 0.784 meters per second. The negative simply shows direction of motion is in the negative x direction. I then also set initial ball position vector 0, 0, 0 to show it started at the origin, and the initial velocity ball.vel is negative 0.78, 0, 0, showing no motion in the y and z direction. Use the time step of 0.01 seconds, ending at 0.474 seconds. After running the Python program, the following simulation was generated, which would be on the following slide. A straight line with a negative slope on the graph indicates constant negative rate of change of position versus time, therefore constant velocity in the negative x direction. Here is a cropped screenshot of the output from my Python program. The top part shows the motion of the ball from right to left starting at the origin, and here's the position versus time graph. This is a graph showing the comparison of the model prediction versus experimental data. The blue line shows position versus time graph from the experimental data, and the red line shows the same graph, position versus time, for the model generated output. What if I chose the orientation of the axis in tracker so that the direction of motion was in the positive x-axis? My position generated, the data generated by tracker would have been positive numbers, and hence the velocity would have simply been positive. The x position versus time graph would have been in the first quadrant, showing the same data on a straight line with a positive slope. I would have changed the initial velocity to the same magnitude but positive value in Python. What does the graph mean? I began to program my model under the assumption of constant velocity motion under ideal scenario with no net forces acting on the ball. And so I had set f net to 0 in on the Python code. Also use the first two readings from the experimental data to initialize the value of the initial velocity in Newton's equation. However, the graph for experimental data clearly shows the effect of some hidden forces that may have caused the ball to slow down slightly. The most obvious of these must be the Earth's gravitational pull, friction between the floor and the ball, air resistance, and drag. Is it possible to say how many pushes and pulls might be added to give a zero or close to zero net force? I don't think so, since ambient conditions such as air conditioning and other factors might create varying amounts of air resistance in the indoor space. Another reason why the experimental data might not always perfectly fit with the predicted outcome may lie in the data gathering process itself. In order to generate position versus time graph in tracker, one has to track the motion frame by frame by manually marking the center of the point of mass to one's best ability and visual judgment. The point selected by the experimenter may not be the exact center of the tracked object. So I would call this a human error contribution to the variation in experimental versus model data, besides the physics-related reasons that I already talked about. For the conclusion, I will say I began with the assumption of a scenario with zero net forces to simulate a constant velocity motion model using Newton's second law, assigning F net equal to 0. So the second term in the equation shown here had no bearing on the motion of the ball, making final velocity equal to initial velocity. But in the experiment, we saw that the velocity of the ball changed due to the presence of unnamed forces such as gravity, friction, and air. I don't mean such as, but gravity, friction, and air resistance being the ones that we do know about, that created an effective net force on the squash ball in the direction opposite to its motion. Hence, the ball could not maintain a constant velocity. Thus, a computer-generated model could assist in understanding the effects of different values of net force based on the momentum principle, Newton's second law in other words, by simply changing the value in the program code to predict outcomes of real physical experiments as close to the real data as possible.